Hello. In this video, I will be talking about some set of rather technical algorithms concerning combinatorial objects. Well, I called the video generating combinatorial objects, but we will be doing not only generating them, but also solving several different tasks about some set of combinatorial objects. So what will be happening? We will have some set, say S, of objects described by some property. Uh, for example, we will have specific sets that are good for examples for teaching purposes. So one of the possible set is strings over some alphabet. Well, sigma is the usual letter for alphabets, so it may look rather hard, but it's just strings with specific set of letters. So, for example, strings with letters A, B, C, or thinking numerically, it can be just strings with letters 0 and 1. And I would say, yeah, and by the way, those will be of length, of some specific length. So some good examples would be binary string of length 3. So it's like 0, 0, 0, 0, 0, 1, and so on up to 1, 1, 1. So we are talking n equals 3. The alphabet that we are allowed in these strings, that these strings are allowed to have, is set of letters 0 and 1. And so we will be talking about this set of binary strings of length 3, for example. Or the main principle of this lecture is that I really don't depend very much on the set that I'm working with. So it can be another combinatorial set, and my algorithms will be more or less the same. So another very famous example is permutations of length n. So the arrays where all numbers from 1 to n are present exactly once. So let me show me once again with the length n equal to 3. It will be 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. Those are all the possible permutations of size 3, that is arrays with all the numbers from 1 to n present exactly once. Also quite an important combinatorial object. And there are many examples. I can think of many more specific or interesting types of objects, but for any such set, we will be able to solve several problems, several tasks. So this lecture has kind of a rectangular structure. So I can think of many different sets, combinatorial sets, and about each set, I can be telling different tasks, solving different tasks. So if I think of 10 different sets, and there will be like 5 different tasks, there could be 50 possible explanations from me, but the video shouldn't be that long. So there won't be 50 parts of the lecture. There will be some, just this rectangle will be taken randomly, and I will show you this task about this set, and this task about this set, and so on. So what is the possible task? What are the possible tasks that we are able to solve about some set? Well, the first very natural one is the cardinality of the set, or simply the size. How many objects are there? This is more like pure math, not algorithmics, not programming. So it's a math task. How many such strings there are? How many such permutations there are? And then comes the real algorithmic part that maybe the main part of this talk today. So the one that I put into the name of the lecture is generating. Generating all the elements of the specific set. So it could be generating all the binary strings in some order or generating all the permutations in some order. Usually, the order would be lexicographical. If you have used the paper dictionary at some point of your life, then you know how words are sorted in the paper dictionary. Or if you compare strings in your programming language by less than and greater than, I'm pretty sure that, well, in this case, you have compared these strings alphabetically or lexicographically. So we are sorting the strings or arrays first by the first object or letter, and then if the first letters are equal, then we are sorting by the second letter, and so on. It can be applied to strings, sorting by letters, first, second, and so on. It can be applied to arrays, sorting by first element, then by second element, and so on. Some programming languages like Python even consider this to be the comparison of arrays. So you can compare lists in Python, and it will be one list will be smaller than the other according to this lexicographical rule. So usually people generate such objects. Well, often it's easier to teach you to generate some objects in lexicographical order. And then there are also interesting tasks of the following kind. So we can, when we know the number of the objects of the set, we can give these objects numbers. Well, probably here I would really insist on programming style indexation, not mathematics style indexation. So this is like object number 0, number 1, number 2, number 3, number 4, and number 5. If you really need to start enumeration with a 1, of course, you can just apply the plus minus 1 to the correct place in the code and have it enumerated by starting from 1. So for example, this enumeration, we can solve the following task. We can take the object and from the object retrieve its number, or we can in this enumeration. So what is the number in the entire list of this permutation? So you are given a permutation, find its number in the overall list, and vice versa. Given a number, what is the 15th permutation with n equal 10? I don't know. What is the object number x among if all the objects of this set are sorted lexicographically? Those are two interesting mathematical tasks. And the last task I will mention, or two tasks actually, it's generating the next, or it's almost very usually it's as hard as the next one or previous object. So there is, when we introduce the order, for example, a lexicographical order of all the objects, it's interesting to take some object and to find the procedure, a short procedure that gives the next object in this order or the previous one. Of course, these two procedures should work, should be reverse of each other. So taking this function and then taking this function should always give you the original object. Okay, so this is our plan. This is our possible couple of sets. There are more combinatorial objects that you can apply these tasks to, and we will be solving them. But before we start doing specific tasks with specific sets, let us make sure that we can reduce some of these tasks to other ones. It will be rather slow or maybe sometimes dumb or stupid, but still, why not? So imagine you have already generated the entire list of all permutations or all binary strings. Then, when you have this huge list, and in many cases, its size will be exponential. So it will be, if you take n like 10, the list of all the objects of size 10, in many cases in this topic, can be like 2 to the power of 10 or 10 to the power of 10, something exponential. So you take this long list, but if you already have this list, then many of the tasks are easy. So you can just take the length of this list and know the number of such objects, or you can just iteratively, with a linear search, find your object in this list and then just see its number. If you have done this, then the very slow but working procedure for like all the other tasks is quite easy to understand. You search over all your objects and then you find the number of your object. Or for example, this one, it's even easier. You have the list of all the permutations and you just go by the specific number in this array and you see the object with this number. So this is just taking the element from the list. Very easy. And also when you have found your object, you just can take the next one or the previous one inside this list, just previous index or next index. So if you are okay with exponentially like very long solutions of these three problems, and actually this one, then you really need to learn the generation procedure. And then once you have generated all the objects in an exponential in a very long time, you will just write a very simple code that solves these four tasks. So these four tasks are there if you need them to be solved quickly, like generate the next permutation without generating all the permutations. And that's where the tasks become quite interesting usually. But if you're okay with exponential time, then just learn the generation procedure. Okay, let's start applying some of the tasks to the sets. So cardinality, it's usually the just mathematical thing, no programming, no computer science, sometimes in simple examples. So if our alphabet, our set of letters has size A, for like from the first letter of the word alphabet, so then you have a possible string of length n, and in first position you are allowed to use one of A letters, in the second position you are allowed to use one of A letters, and so on. So for each selection of the first letter, and there are A possibilities, you have A consecutive selections of the second letter, for which you have A consecutive letters or selection of the second letter, and so on, up to the last letter. So therefore, the number of choices, it's dividing by, the number of choices multiplies by A with each position, and so the formula is A to the power of n. And of course, it's not easy pure math, because if you have thought how many bytes are there, how many values can be stored in a single byte, you of course have solved this problem, because there are 8 positions, so n equals 8, and each position is either 0 or 1. So 1 bit is either 0 or 1, so a byte is exactly this task, string of length 8, where each position can be filled with a 0 or a 1. Therefore, the number of possible values of a byte is 2 to the 8, it's 256. And so on for any similar thing. And so it's in simple examples, it's math, not programming. And for permutations, let's also make sure we understand the similar calculation. So if you're talking about an array of length n, where all integers from 1 to n should appear exactly once. So for the first position, you have exactly n possibilities. Any of the 3, for example, here, integers can be put into this place. But then when you fixed a specific first number, what is the number of possibilities for the second position? Well, you can apply any integer from the set 1 to n, except for the one you already used. It will be different set each time. So when you apply the 1, you can use a 2 or a 3. When you apply the 2, you can only use 1 and the 3, and so on. But for any specific first number, there are exactly n minus 1 possible values for the second letter. And for the third letter, you can use any number from 1 to n, except for the two numbers that are already used to the left of this position. So there are exactly n minus 2 possibilities for something to be put in the third position. And indeed, once you have done, for example, 1, 3, there is exactly one possibility for the last digit for the last element of this array, and so on. And interestingly, so I have shown you this over here, the last position has exactly one possibility to be filled in with, because you have used all the numbers from 1 to n except one in the previous n minus 1 positions. And so exactly one point, exactly one number is left over to be put over here. So a permutation, indeed, once you have filled in all the numbers except one, the last number is deterministically can be found from the previous elements. So there is exactly one option to select this element. And so this is the formula, the product of numbers 1 through n. This is exactly by definition factorial of n. So the number of permutations of size n is n factorial. All right. Now let us, so this was an example of calculating the number of the cardinality of such sets, or the number of objects in each set. And now let's do maybe the main part of the talk, the generation procedure. Interestingly enough, I will try to write, I will erase, unfortunately, this part, and I will write the code that works, tries to be as general as possible. So actually, this is the name of the subtopic, generating combinatorial objects, and I will try to teach you I think Python. It will be not pseudocode, it will be almost exactly Python code that will be as general as I can to let you generate very different combinatorial objects. But let's start probably with strings. So I shouldn't have erased it. Strings over some alphabet sigma. So indeed, people use the word over, strings over some alphabet. So let's generate all the strings of length n that if we are allowed only such and such letters or digits, it's really not important, or like emoji, any characters you want. And it's usually like free or cheap to also add the condition that the objects are generated in the alphabetical order or in the lexicographical order. So we will first generate the objects with the first letter, like let's say at letter A in the first position. It will be a huge set of objects probably, but then only then we will generate the set of objects with letter B on the first position, and so on. Like in a printed dictionary, first a huge part with first letter A, then a huge part with the first letter B, and so on. Our code that I will write on the board will be recursive. That is our function. It will be one function that is allowed and that will actually run other instances of the same function. So I want to write down a function that solves this task, but as you remember from recursive functions topic, it's usually some function with a parameter, like you want to recursively calculate n factorial. You probably had exactly this example on that lecture. So you wrote the code for generating n factorial where n was the parameter of your function. And then it probably, with high probability, used the value of some smaller factorial. So it ran the same function with smaller parameter. Like solve a smaller problem. So your function was employed to solve some large problem, and you sub-employ a copy of your function to solve a smaller problem, and then you use those results to calculate the answer for your level. So your recursive function on some level runs the same function on a smaller level and uses those results to solve the problem of its level. That's what the recursion is sometimes about. So now we want to define over here this thing, the solution of some level. And here, so we really need to find the formulation of this function that allows us to run the same function for smaller instances of the problem and reuse its results. Here's the good solution. Let me write the Python code. This is the system, the approach that works really well for many different types of combinatorial object. So it's really not important which, some people write in different orders, but in Python, it's good to have the prefix argument second. I will explain later why so. So the word prefix means, as I hope you know, the beginning of some array. So the first several elements of some array is called prefix. And this is the ideology of the function that we are to write. Actually, I can write it as a documentation. Yeah, why not? So I will be writing the function that generates, or maybe in our case, prints or processes. It's really not important over here. You can do it in the end. So it generates, or in our case, it will simply prints, generates all the objects of length n, starting with this prefix, with the given prefix, with the given prefix. So we generalized our task. We were employed, we were asked to simply generate all the strings over the binary strings, for example. Let's, for simplicity, say binary strings of length n. So we were obliged to simply generate or print all the binary strings of length n, and we kind of made our problem a little bit harder. So we complicated the task for ourselves, but once we complicated it, we can reuse our function recursively, and that's really the brilliance of recursion. So we say not only we'll be able to generate all objects of size n, all binary strings of size n, but we'll also be able to generate all the binary strings starting with this specific prefix, well, of some length. So for example, if someone runs our code with length 6, n equal to 6, and this prefix, we will generate all the binary strings that start with this prefix, and there are obviously 4 of them. So we will generate this prefix plus 0, 0, this prefix 0, 1, this prefix 1, 0, and this prefix 1, 1. This will be the generation of all the binary strings of length n, starting with this prefix. So, for example, the overall task is definitely to generate all the objects of length n, starting with an empty prefix. So if you give your function, if we give our function the empty prefix over here, it just means, okay, generate all the objects of size n. So this is the usual way to run our function. But we can also run our function in a smarter way with the specific prefix. Okay, this will be a recursive function. In the recursive function, I really advise you to always think about the special case, the specific small case in which you don't need any recursive call. Obviously, if your function always runs at least one instance of the same function, then it cannot theoretically finish. So there must be some specific case, some small case or extra case, extremal case, in which you don't run another copy of yourself. Otherwise, you are definitely doomed to Stack Overflow problem. Or in like theoretical infinite computer, you are doomed to infinite recursion. But in real computers, to Stack Overflow. So when this task doesn't need any subtasking, when you as an employed worker do not need any sub-employees, well, if you are to print many objects recursively, well, then the idea, I didn't tell you yet, but here's the idea. Of course, it's a good idea to recursively employ another person, like another contractor, to solve the problem with some prefix of this size and different letters or digits over here. So once there are possibilities of different letter or digit over here, the idea is to do a recursive call with different letters over here. And when there is no space to run to employ sub-employees, to employ subcontractors, if your prefix has already eaten up the entire space of n elements. So if you are hired to print all the objects of your type of length n, starting with some prefix, and the prefix already has length n, well, then your task is so obvious that you don't need sub-employees to help you. So this will be our first specific case without recursion. If length of the given prefix has already reached the level n, then your task is simple. You are asked to generate all the objects of length 6, starting with 0, 1, 1, 0, 1, 1. There is just one such object. There is no thinking to be done. It's already there, and the list prefix already has exactly this object. So we are just going to process this object, and I'm going to do the bad thing. I will simply print it to the screen, which makes this function not pure. It's like a dirty function that prints something to the screen. It's a bad idea. Well, I'll write it in the comment. So I will just simply print the prefix to the screen, and I understand that this is kind of like dirty, but who cares for current teaching place. So in a good code, you don't write code that has this extra effect like prints to the screen. You rather save it to some array that you are given, or yield it if you know the generator functions. But here we are just doing the processing of this prefix of this object that we received. So it can be print if we are okay with printing all of them to the screen, or if you are doing some iteration over all the interesting objects, you like check this object or process this object. So here you will run some other function that does the actual work with the next and next and next objects. So you run a function that processes the object, and here you run that function. For example, print it to the screen. And you don't have to do anything else in this case. So once you, in this case, if you are asked to generate all the objects of size n with the prefix of length n, here is the object, process it, finish your job. So the subcontractor of this level is really a stupid person who just does his work by return by processing the prefix and finishes the work and receive the salary. Why not? So here comes the main place. If we came to this place in execution, therefore we didn't run the return operator, and so the length of the prefix was smaller than n. Well, if somebody runs you with prefix larger than n, the length of the prefix larger than n, then it's the problem of the one who called this function with the stupid parameters. So in Python, you understand that you can be run with stupid set of parameters, like someone could give you a floating number over here and file over here. That's their problem. So we believe that we are run with prefix of length no more than n, definitely. If it's exactly n, we finished. So now the prefix is shorter than n, just like in this case. In which case, all we want to do is to hire smart and correct sub-employees, subcontractors to do our job. We will like almost do nothing. We will be just the bosses of the certain level that employ subcontractors to do the actual job. Now, what subcontractors are we to hire in this case? Well, the binary strings that start with 10 or with 0110 are those who have a 0 over here and those who have a 1 over here. In which order do we print them? Well, I told you that generally in this topic, people like to print objects in alphabetical order. So let's first print all the guys with a 0 here, and then print all the guys with a 1 here. But what is this phrase? Print all the guys with a 0 here. We could have done the job manually by our hands on this level, but this is exactly what can be done by this generalized function. We wrote a generalized function, very generalized function, which allows us to use this on many levels. So generating all the elements with a 0 over here is exactly a task for our function. So let's not do anything smart on our level, but rather run our function or hire a subcontractor with this very specific task. And that's the main idea of generation of combinatorial objects. You iterate over possible letters or digits in this position, and for each specific letter or digit, you say, okay, I've got a new interesting prefix, let somebody of the next level print all the objects with such prefix. So what you do is iterate over possible letter, say x, on this level. So we say for x in our task, it's in alphabet. So let's say that there is a string or a set of characters called alphabet. Well, sigma or sigma large, but capital sigma, but alphabet is okay. It's even easier to read. So we iterate over all possible letters, and each letter over here can be the next letter. So our prefix can be appended with any of these x values. So I will rather leave some space over here, and then write the important line. We just hire a subcontractor. We ask another copy of our function that we are actually writing. It's normal for recursion to solve the problem with this prefix. So n definitely doesn't change. You can make n a global variable, but I'm against global variables, so let me not do it in the code on the whiteboard, although writing dirty print over here is also against my principles. However, I do the bad thing. So n can be a global variable, but more beautiful way is to give n to each function as a parameter. And the prefix that I want a subcontractor to work with is our prefix with the letter X appended to the end. So if you're working with lists, Python lists, and prefix was a list, then we can just add an integer to this list or a character to this list. So here really my code, it's a Python style, you know. If the alphabet was a list of letters, characters, then it will be a list of characters and it works. If alphabet is the list of integers, then this will be a list of integers and it also works. So it's a we are using the Python has dynamic typization and typing, and so this really doesn't depend on which types we have. So let me think about the current code. It works. The current code will on each level try to apply different letters to the end of prefix and ask the same function to generate all the strings that start with that prefix extended by this character X. And when this prefix runs up to level, like takes already all n positions, then we simply print it to the screen and return. I hope that if you write this, you will receive, yeah, I think I didn't do any mistakes, and you will receive the printed list of all the binary, for example, well, depending on what you put over here, it will be the list of binary or strings over English capital letters or whatever. Well, over here, since I wrote a list over here, I'm using lists. Here you will have a Python style list printing, like with square brackets and commas. So probably over here you can join this list with an empty space or something. So pretty printing is up to you, but the general thing works nicely. And here is another. Now, what's special about this code? It's rather general. So take zeros and ones here, you will receive binary strings. Take English alphabet over here, you will receive all the words of English alphabet of certain length. Even permutations are almost done by this code. So let's do the permutation. Let's solve the task of generating 4 permutations. And here is the situation. So, for example, once again, we have a, well, let's say that the prefix is of size 3. So we have a 4, a 2, and a 1, and 3 more places. And as you can see, n equals 6 as before. So we are hired to print all the permutations, starting with 4 to 1 and having length 6. So someone ran our code, executed our code with prefix 4 to 1 and n equals 6, equal to 6. Well, first of all, if this code simply stays the same. So if we came up to the prefix 6 to 1, 5, 3, or 4 to 1, 5, 3, 6, like if we have finished generating the prefix, and we are asked to find all the permutations with this prefix of length n having length n, then the only permutation that starts with this prefix is, of course, only this prefix, and we print it and we finish. So this code is universal, very good. And note that I didn't write generate strings or generate permutations. The name of the function is also universal, like generate. And the words prefix and n are also universal. So this stays the same, but what x values are applicable to this position? So once again, when we have this specific prefix 4 to 1, we are iterating over all possible next digits, next letters in this position. And now something smart happens, because it's a bad idea to put a 1 or a 2 over here, but it's normal to write 3 over here. So what do we do? Well, you can make it optimized and like super fast, but a very normal starting place is to write the same code over here, So you iterate with a variable x over 1, 2, and so on, n. So here you just write the range 1, comma, n plus 1. So you iterate over all possible digits. And yes, indeed, I will iterate over 1 and the 2 and the 4 over here. But I don't want to run my code with prefix 4211 or 4212. So I don't want to write this code with bad x. And that's all we need to do. We need to write over here if, and here comes the pseudocode. If x is bad, then simply continue. And that's it for the general code. So in some cases, there are no bad x values, like in binary strings. Over here, we can put a 0 and a 1. It always is friendly with the previous prefix. There are no contradictions. There are no enemy situation. And so all the x are good, and you don't need this if. But in smarter implementations, all you have to do is to rule out, to forbid the x values over here that are not friendly with the previous prefix. There are some smarter tasks where it's some hard math, probably, and there are some easy tasks where it's just a simple condition. In our case, you only need a simple in operator. The Python language has in operator, and all you need to do is to find whether x is in the prefix. X in prefix. So if your digit n, x, is 1, 2, or 4, it is present in the prefix, and you do not run a subcontractor call to the prefix 4211 or 4212 or 4214. But if x is not present in the prefix, like 3 or 5 or 6, you run this code with prefixes 4213, 4215, and 4216. So you will run exactly the good subcontractors that will eventually fill the prefix array up to the length n and receive the correct permutations. So the same code with a little bit smart red implementation over here also allows you to generate all the permutations of size n. And if you will be solving some other mathematical task, I'm really quite sure that the code will be quite similar, just the most complicated thing will be to iterate over here only by the good x values, which is usually a simple for loop over all the possible x values, and a smart exclusion of the bad x values that do not fit into the previous part. So this is usually the only smart code you do in this place. And otherwise, this is the general code that's just working for generating combinatorial objects of many different types. Okay, so now you can iterate over all the possible binary strings, for example, with this code, like 1, 0, 0, 0, 0, 0, 1, and so on to 1, 1, 1. Or you can generate all the permutations, 1 to 3, all the way to 3 to 1, or some larger examples. And let me make a break, like inside this talk, and show you the examples where you want to do this iteration, where you want to code such function and to generate all such objects or such objects and so on. This is really helpful if you want to check all the possibilities of some combinatorial problem of some search over such kind of objects. Well, let me just give you some examples, some metaphors. So, for example, you are trying to kill some bad bacteria, and you don't know what set of drugs helps you kill this bad bacteria. So this first digit will encode whether you use drug number like drug A, this will be about drug B, and this will be about drug C. So 000 will be like using no drugs. Well, it will not kill the bacteria, but you can spend this experiment. And this is given all the drugs to the petri dish with bacteria, and this is like giving only drug C to the bacteria, and so on. And you don't know what set of drugs is best to be used by to kill the bacteria. So you run this set of modeling experiments in some order. So you try mathematical modeling of the petri dish with the drug, with this set of drugs, and so on. And you iterate over all possible sets of drugs. And for example, you calculate which set of drugs is the fastest to kill the bacteria in the mathematical modeling. And so you know the best set of drugs that you will use in real life in production. So to iterate over all sets of all subsets of some set, this is exactly the code. Now, you have not only drugs, but you have some medical procedures, like you can apply heat or apply ultrasound and so on. And you know that applying all the procedures to the petri dish with bacteria is a good way to kill the bacteria, but you are not sure which order is best. So maybe you should apply the ultrasound first and then the heat, or the other way around. You don't know. So you want to find the best order of the procedures that kills the bacteria as fast as possible. And here comes the permutation generation. You generate all the permutations, and you try this order and this order and this order. And for each order, you apply the procedures in this very order in a mathematical modeling of a petri dish. So you do the mathematical modeling of this order, and you just collect the information which order kills the bacteria the fastest among all these mathematical modeling iterations. So you try all n factorial permutations, you do mathematical modeling of each one, and you select the best order. So in order to find the best subset, you can use the generation of binary strings. In order to find the best order, you use the same code to generate all the permutations or all the orders of some objects. So this is a general code that helps you search combinatorial, like make a combinatorial search among many possible options like this. All right. Yes. Mhm. Now let's, as I proposed, solve the problem of uh, moving from the object to its number and vice versa. So let's make it for permutations, for example. Let's say that we have some permutations like 6 to 1, 5, 3, oh, 4 to 1, 5, 3, 6, and we want to move from this object to its number in the overall lexicographical list of all the permutations. Once again, so we start with 1, 2, 3, 4, 6, 4, 5, 6. We end with, okay, so 6 factorial is what? It's 720. So the 719th object is 6, 5, 4, 3, 2, 1. And somewhere in this list is this order, and you want this permutation, and you want to know what is the order of this permutation. Yet another mathematical task that, once again, like almost a joke, is that you can generate all the permutations, find this object in this array, and return the index. So in 6 factorial operations in this very long procedure, you can solve the task. But of course, we will not spend the algorithm that I'm teaching you is not about spending 6 factorial operations, but rather doing some simple mathematical stuff to find this answer, to find the number of this guy in the list of all the guys. And here's a wonderful theorem, like huge theorem. It says that your number in programmers' enumeration, like computer scientists and programmers enumerate from 0. And so in this enumeration, your number, like number 5, is the number of objects that are strictly smaller than you. Like if you are number 5 in programmers' enumeration, then there are 5 objects strictly smaller than you. Okay, very smart theorem. So I will not be doing this. I will not be finding the number, the index of this object among all the objects. I will be solving, according to this theorem, the other task. How many permutations are strictly smaller than our? So for this permutation, there are 0 permutations that are smaller than our, and for these permutations, there are 719 permutations that are smaller than our. Let's solve this mathematical task. So how can one array be lexicographically smaller than another array? Well, to be lexicographically smaller is to be equal in several positions from the left, and then in the first differing position to be strictly smaller. So to be smaller than our permutation P is the only way to be smaller is to be equal in some first set of letters, indexes, for example, 0 or 5 maybe, not 5, but maybe, and then to be smaller. Okay, let's count all such guys, all such permutations. Well, some of them have the first position of being different, some of them have second position of being different, and so on. So let's iterate over this position and calculate the total number. Well, the first way to be smaller than P is to have very first letter being different. So like, well, how can a word be before the word whiteboard in the dictionary? So it can have a first letter smaller than W, or it can have the first letter W and the second letter smaller than H, or it can have first letters WH and third letter smaller than I, and so on. These are how words can be smaller than whiteboard. So how about being smaller in this position? Well, let's count all such guys. Here you can put any number 1, 2, or 3, and if you put such number, you are already smaller than the permutation. And so there are 3 possibilities over here. And once you have put this number over here, the number of possibilities for all the other 6 numbers is the number of orders of the 5 numbers in 5 positions. That's exactly 5 factorial. So once you have, for example, selected 2 over here, there are 5 other digits that can be put over here, and any order of them is okay. So 5 factorial orders once you have selected a 2. And once you have selected a 1, also 5 factorial orders. And once you have selected a 3, also 5 factorial orders. So the number of such guys smaller than us is 3 times 5 factorial in this example. Okay. Well, there is another way to be smaller than us, than P, is to be equal in this position and to be smaller in the second position. Well, if we are equal here, we have a 4 over here. And if we are smaller than 2, then definitely we have a 1 over here. So there is one possibility for the digit over here. And once we have put this digit over here, there are 4 factorial continuations to fill in these numbers, because 4 and 1 are already put in place, and 2, 3, 5, 6 can be put into these positions in any order. Okay, another possibility to be smaller than P is to be equal in this position and smaller in this position. Well, there are zero possibilities of D. So this is a 2. And here are zero possibilities for a digit. So we have a zero possibility. And formally, for each of the zero possibilities, you can have 3 factorial continuations. So this is a 0, but written mathematically smartly. And here comes another good example. So let's finally talk about the general formula. How these 3 digits are equal to p, and how many ways are there, how many permutations are there such that the first 3 letters are equal to p to the corresponding digits of p, and this digit is smaller than corresponding digit of p. Well, here's the final answer. So you need to take any digit smaller than 5, but you are not allowed to use this digit. So finally, the general formula for this amount of possible digits is just this number minus 1, so any number from 1 to 4, except for those of them who are already present to the left. So you do this simple like for loop or even smart procedure with sets or a for loop and calculate that over here there is one possibility, only a 3 can come to this place. So there is one possibility for a digit over here. And once you have selected a digit over here, there are 2 factorial continuations, because once you have put a digit over here, 2 digits for 2 places, there are 2 factorial ways to do this. Now, another way is to do this. So we can be smaller than p in this position. Well, here it's once again 0 possibilities, because there are no digits smaller than 3 that are not used to the left. So here we have 0 times 1 factorial. And formally, we can, maybe as a joke, maybe seriously, speak about this situation. So in fact, you can omit this situation because you cannot be equal in 5 positions and be smaller in the last position, because the first 5 positions determine the last number definitely without any choices. So you will definitely have a 6 over here, so you can be smaller only in this position. But so you can either omit this part or formally write 0 times 0 factorial, which is also a correct code over here. So the last term will always be like this. And then you sum up all these numbers and receive exactly what we needed to find: the number of permutations that are smaller than p by this way or this way or this way and so on. And the number of permutations that are smaller than p is exactly the number of p in the overall list. So this was the number of our permutation in the list of all permutations sorted lexicographically. All right. Now in the same list, there are many permutations numbered from 0 to 719, and the opposite task is to find the permutation which has the following number. So once again, as a joke, we can generate all the list in exponential time and just take the element number 566. It's a joke because it's exponentially long time taking. And the serious work is to find the array of size 6, looking at this number in a short procedure without doing 720 printings or something. Well, so let me write it down below. So this is the number of the guy we want to find. Okay, let's do it from left to right. And we will find the permutation with this number. And the good idea is that we will count. Oh, once again, we will count the permutations that are smaller than than the desired one. So we will find the permutation such that there are 566 permutations smaller than it. But we will do it in huge blocks. So we will like omit many permutations by taking the entire block, the entire part of all the permutations with one huge movement. So we will not count one by one up to the object number 566, but we will do it in huge blocks. So lexicographically speaking, what is the first huge block of permutations? It's the guys that start with a 1. And how many are there? Well, it's not hard, complicated math. So we can, when we have fixed the 1, there are 5 factorial possibilities to fill in the rest. So there are 5 factorials or 120 possibilities for the continuation. And what are the and this is the lexicographically first block of permutations. So what are the numbers of these blocks? Well, there are 0 to 119. Okay, does our number fit into this range? If it did, if we were like searching for permutation number 66, then it's even easier because we can just write this one in a permanent marker. I don't have one, but like use the permanent marker over here and continue solving, knowing that this one is a correct digit because the permutations that start with a 1 have such interval of indexes. Our index fits into this, and let's continue. But our index doesn't fit into this range. So there are 120 permutations, first permutations, that we can remove from our interest in a single movement, in a single hand wave. So we are not interested in these guys at all, and therefore we can subtract the first 120 guys from our interest. And now, among all the other guys, we are searching not for permutation number 566, but for permutation number 646. So we removed 120 permutations from our area of interest, and in the rest, this is the index of our interesting desired permutation. Now the next block is the ones that have a 2 over here. Well, they also have these numbers, these indexes, and our desired permutation has this index. So 446 doesn't fit into this set, and we can omit all of them. And we are now searching for the element number 326, and we move to these elements. Once again, these elements are, there are 120 permutations starting with a 3. Our index doesn't fit into this set, so remove all such guys. And we are searching for the element number 206, and let's search in this block. Once again, we don't fit into the first 120 elements, so let's search for the element number 86, and let's search in this block. Okay, finally, in this block, the elements have numbers 0 to 119, and we need to find the element number 86, so it indeed fits into this block, and this 5 can be written down in a permanent marker. So this 5 is definitely the correct answer, and among such permutations, we are to find the object number 86. Okay, once we have drawn this digit with a permanent marker, we start iterating over the next digit. Well, some permutations start with 5, 1. How many are there? Well, those permutations have 4 more objects to be ordered in some way. There are 4 factorial such objects, and their numbers are 0 to 23. Does our index 86 fit into this set? No, we are not in this block. So we can collectively remove the entire block with one hand wave and say that we move to the next one. And so we remove 24 permutations collectively. And so the number that we are seeking right now is not 86, but 62. The guys that start with the 2 have these indexes, 62 doesn't fit. So let's move to the next block. And we are now interested in, so we collectively removed 24 permutations. So we are now searching in the rest of the area of the interest. We are searching not for number 62, but for number, what's that, 38. Does this guy index fit? No, it doesn't. So we move to the next block and we omit 24 permutations from our area of interest. And so we're interested in number 14. Okay, number 14 fits into this set of indexes. So we can draw a 4 in a permanent marker. Okay, and we need to find the 14th permutation with this prefix. Okay, it can start with a 1. How many such permutations are there? Well, we are to put 3 more objects, which is 3 factorial ways to do it. So 6 possible continuations. And the numbers are 0 to 5. Does 14 fit into these indexes? No. So we remove collectively 6 permutations, move to the next block, and among all of the permutations, we are interested not in number 14, but in number 8. Does number 8 fit into this block? No. So we move to the next block, and we are interested in the permutation number 2. Does number 2 fit into these indexes? Yes, it does. So we can draw 3 in a permanent marker. Okay, we are interested in block in permutation number 2 with such prefix. Well, there is a block of such permutations. How many are there? Well, we are to put 2 more numbers, so it's 2 factorial, which equals 2, and their indexes are 0 and 1. Does permutation number 2 fit into these indexes? No. The indexes of these guys are 0 and 1, and we need the permutation number 2. So remove the entire block, and among these guys, we want the zeroth permutation, because we wanted permutation number 2. Before that, we collectively removed 2 permutations, so now we need the permutation number 0 among the rest of the permutations. Okay, number 0 fits into these indexes, so we can use permanent marker to draw a 2. Okay, among these permutations, we need to find the permutation with index 0. Well, some of them start with a 1. How many are there such permutations? Well, 1 factorial, which is 1 such permutation, and the indexes of such permutations are 0 to 0. We need to find permutation number 0. Such guys have numbers 0 to 0, so our 0 fits into this 0 to 0 range. So 1 is a good block. We dive into this block. We draw this this one in permanent marker. So there is a block that starts with a 6. How many permutations start with this prefix? Well, formally speaking, it's 0 factorial, which is 1. And the indexes, the numbers of these guys are 0 to 0. Does our number 0 fit into these indexes? Yes, it does. So this is indeed a good block that we like. So we draw this 6 in a permanent marker, and this is the answer. So for each digit, we tried to put here 1, 2, 3, and so on up to above, and we thought about each digit. We found the indexes of permutations that start with this prefix. If our desired number fit into this range, we say, okay, this is the good block. But if it doesn't fit into this range, we remove the entire block and subtract the size of this block from the desired index and continue the process. So in a very short time, like 6 squared or something, we will find this final permutation number 566, which is a cool task without exponentially printing all the guys. All right. And the last task that I promised to solve is printing the previous or the next. Well, for example, permutation. So I'm really doing a lot of explanation about permutations. If you need similar, the same tasks applied to other combinatorial objects, well, please use analogy, use your brains to find the formulation of the same algorithm applied to different combinatorial set. But for the ending of this lecture, let's find the next permutation. So like 6 to 1, 5, 4 to 1, 6, 5, 3. Why not? Why not? So we have some permutation, the current permutation P, and the task is to find the next permutation in lexicographical order. So I will be just telling you this part because finding the previous is usually absolutely symmetrical. So you will just repeat the same logic and you will be able to find the algorithm for finding the previous one. But I will tell you how to find the next permutation and hope that you will be able to find the analogy for different combinatorial objects and also for previous and not next object. Okay, how can we be next? Well, what is the way for 10-letter word in English to be the next word to the word whiteboard? Yeah, in English dictionary. So to be larger than whiteboard in English dictionary, you have to be equal in some first letters and then be larger than whiteboard. So one possibility is to have the last digit, the last letter of the word whiteboard increased. So if there is a word whiteboards with a Z in the end, if it was a correct English word, then it would be really next after whiteboard in the English dictionary. So if you have like this permutation, maybe even like this. So one permutation that is larger than our P can be like this, but another permutation that is larger than our P can be like this. Which one comes closer in the dictionary of all permutations to our P? Well, of course, this one, because it fits into the block that starts with 4 and 2. So it's the same block of permutations, and it's closer to P than this one. So in order to be the next after P, you want to be larger than P, but you want this position of being larger to be as right as possible. And that is not only for permutations. For objects of the same length, in order to be next, you want to be larger than your object, but you want this differing position to be as right as to the right as possible. And so let's try to make it as to the right as possible. Well, maybe we can make the differing position this much to the right. Of course, no. For the permutation topic, it's impossible to be equal in this position and be unequal in this position because the last digit is determined by the previous ones. So it's never possible in any permutation for any permutation P. Now, how about being larger here? Well, it's a good, so I tried to make a good example. You want to have the answer to be 4216 and then have some digit larger than 5. But this digit has to be other than these 4 digits. Well, there is in this, we see that there is no digit larger than 5 that can be used here. So it's impossible to have such position of differing and being larger. Maybe we can be larger in this position. Well, once again, you cannot be larger than 6 at all. So you cannot be larger like this. And finally, can we be larger in this position? Yes, indeed, we can. So what is this position? Well, in fact, we have decreasing, 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 and so on. And this is the position of first increase, first increasing. So this is the position where when we look at the pairs, it's decreasing, decreasing, and finally the first increasing. And that is the most rightmost position where you can find a better digit. So because if there was a suffix, an ending with decreasing, 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 think about it. Any digit is larger than the rest of the digits. And so if you try to increase it, you have to use one of these guys, but they're all smaller. So you cannot increase it. And as soon as you find an increasing, you definitely can increase this digit, for example, by taking this one, but there is more to it. There is more to talk. Because what digit do I want to place instead of a 1? Well, I'm speaking about the next word in the permutation dictionary. So after the whiteboard, of course, there is the word zebra, but there is also word yield. Like you can make this a Z, but it's better to make this a Y after whiteboard, right? So here I could make it a 6, but rather among such words, of course, to be the next one, I want this digit to be as small as possible, but larger than 1. Because why use a 5 if 3 is better, is closer in the dictionary? So the answer is to use the smallest of these digits that is larger than 1. And yeah, so this is the first increase, and this is the smallest digit to the right that is larger than this one. So if this one is a 1, we need a digit larger than 1, but if there are many such digits, the smallest one. And once we put the 3 over here, think about this word. This word that we receive starts with the same letters, it's okay, and then it has a larger letter than our word P. So this word is already definitely larger than our word P. Once we have written this, we know that the received word is strictly lexicographically larger than P. But our task is to find the next word after P. So among these many words, we want to find the smallest one. So any word that starts with a Y is larger than the word whiteboard lexicographically. So the next word would rather be something with YA, something among the words that start with a Y, something that is as small as possible. So we just need to have these rest of the digits to organize a word that is as small as possible. And of course, to make the rest of the permutation, to organize a word that is as small as possible, it's easy to see that you need to use these digits in increasing order. So we take like 1, 5, and 6 in increasing order. And this is indeed the next permutation after our one. And I really believe that this overall algorithm is generalizable for many other combinatorial objects. So you try to make if you want to make the next object, you want it to be equal in the first positions and then larger than your object in some position. First of all, mainly, you want this different position to be as to the right as possible. Once you have found this position that is as much to the right as possible, you want to place, well, these digits are obvious, you just copy these values. And this digit should be as small as possible, but of course larger than your one. So in your object P, not only permutations, any combinatorial problem like this, you find that, so this is the rightmost place where you can make an increase, a larger thing. And among the possible larger things, of course, you select the smallest one that is larger than this object over here. So if many possibilities over here, then take the smallest one, but definitely larger than this one. And once you have put this larger element than those that you had in P, then definitely this object is already larger than your P, and the rest can be greedily generated, like you have to generate the object with this beginning, and all you have to do is to make this object as lexicographically small as possible. Well, often it's quite simple. So here it's just sorting the elements in the increasing order. And yeah, this is the answer. So you also, once again, it was like 6 squared operations. It's very short procedure to find the next one, and you don't have to generate all 720 to find this object and to get the next one. So the joking part would be to make exponential procedure of generating, find this object and take the next object, but this was a serious algorithm over here. Now let's check ourselves. Does our algorithm has any flaws? Can it throw an exception in Python? Yes, it can. I was talking about the first increase, but if you try to search for the first increase and there is no increase at all, then you will have an exception. When does this happen? So it happens in a permutation where this is a decrease, this is a decrease, and so on. This is a decrease. So you have a permutation that goes smaller, smaller, and smaller. And so this permutation is like 5, 6, 4, 3, 2, 1. Well, and it's a good self-check. Indeed, it's very good that our algorithm for finding the next permutation fails or gives exception on this permutation, because this permutation is last in the objective list of all the permutations, and it's mathematically correct that this permutation does not have the next one. So it mathematically doesn't have the next one, and it's very good that our code throws an exception when trying to build the next permutation after this one. So this self-check, we have passed this check. It's good that we sometimes throw an exception, and it should be done on the last permutation. That's exactly what we do. So if you implement the next object function in some other combinatorial set, please self-check. Please check yourself that your code can throw an exception, and it will be done only if this is the last object among the dictionary of all the combinatorial objects that you are working with. All right, so we have covered generating combinatorial objects, counting them, moving from the object to the index and vice versa, and generating next or similarly previous object in the lexicographical order. I really hope that this overall idea helps you to solve not only binary strings and permutations, but other similar combinatorial tasks, and it can be used to iterate over all sets or all orders. So like iterate over exponential space of some possibilities. You have like a lot of possibilities that you have to check, and you have the time to check them. So you iterate over all set of possibilities using this theory, using this lecture, and often using the code that was present in the first part, because the code tried to be really generalizable, really reusable in many situations. I hope that this generalized code helps you in mathematics, in real life, in whatever objects of interest that you have. Thank you for your attention.